So welcome back after lunch. So before lunch, we had Alok talk about the power plants and the emissions, etc. So now I'll be talking about a decade of work in a field called energy analytics, smart meters, etc. And I'll present several research papers through this. I'll start off by showing you a photo. Does anyone recognize this photo? How many? Okay, so this is from a movie called Swades. This was the year 2003. How many of you were born? Okay, not a lot. Okay, I was in class 10th at this time. So this, I don't know if you've now watched the movie or not. It's the story of an Indian origin scientist working at NASA who then comes back to India for some short vacation to meet his family and ends up realizing the problems and then ends up also creating some solutions for those problems and then eventually moves back to India. So as a class 10th student who was almost now going to prepare for JEE, etc., this was a very inspiring moment. This was a very inspiring movie. And this was also the time, so 2003 odd, even though I had been staying in Delhi, 100% power was not available. So we had also used things like gas cylinders. Has anyone used kerosene cylinders here for power? A very small subset of you, right? So we had to use them, although we had inverters also, but still there used to be outages. Sometimes the outages used to be 10, 12 hours also, even in Delhi during that time. But I think the situation has significantly improved in the past decade. And I think Alok also presented a slide on the electrification rates, and the numbers are almost close to 100% now, which was not the case in the early 2000s. So this was one of my inspiration when I started my PhD. This is around year 2012 or so when I started working on my PhD. So we started looking at where is the overall energy going in. So you wanted to say that every person has access to energy, electricity. We first wanted to understand that where is the energy going. We realized that buildings were contributing very significantly to the overall energy consumption. So buildings like this, residential buildings, commercial buildings, manufacturing plants, etc. So overall, they would contribute roughly 30 to 40% of energy across different countries. So therefore, this seemed like a good area to create a dent. If something consumes a lot of energy, maybe that's where we need to reduce the energy so that everyone can get access to energy. That was one way. The other would be you create more energy. You use maybe more non-conventional resources, but this was one approach. So question to all of you now, how can we reduce the energy consumption of buildings? Yes? Not a very difficult question. How can we reduce the energy consumption of buildings? Better architecture, okay, good. So when was this building constructed? This was constructed in 2016. When do you think this building will next be changed? Next be again broken down, built again? 30, 40, 50, 60, 70 years. So architecture is a good way for newly constructed buildings, but let's say 70, 80% of the buildings which will exist in the next 30, 40 years are already built. So therefore, architecture is a solution, but not the only solution, especially for the buildings which currently exist. What else could we do? How can we reduce the energy consumption of buildings? How many of you knew the government initiatives where they were highly encouraging the usage of LEDs? Like, has anyone now seen the old fashioned tungsten bulbs? It will be very hard to now get. It will be probably more expensive than the LED lights these days. So this is another area in which you can reduce the energy consumption of buildings, which is to produce more efficient technology. You have also seen how the air conditioners have, which were largely previously purely electrical devices. Now they have a lot of significant electronic component. So that's another way. What else could we do to reduce the energy consumption? Yes. Okay. So So you all come in at around 9 a.m. or 9:15 a.m. even though the session says 9 a.m. When do you think the air conditioning starts? So you might be surprised, not here. Here it's, I think, already very efficient. But in certain places where the offices might start at 9, the air conditioning might start at 7. So a lot of that cooling is not needed. Similarly, if your office ends at 6, do you need to have the AC working full blow on till 6 p.m.? No. Probably you can turn off or wind down by 5:30 p.m., 5 p.m. or so, because all of that cooling is then wasted. So that's operation efficiency that we can get. You can bring in better appliances, you can bring in better architectures. These are different ways in which the energy consumption can be reduced. There is yet another one, which is feedback based energy consumption. So there have been various studies done on how energy can be reduced. One was a very interesting study. I think this was done in the UK. They gave different kind of feedback on how on your energy consumption. Things like, if you reduce your energy consumption by 5%, 10%, maybe you'll reduce the number of trees being cut. That was one, number of trees being cut. Second, the number of rupees, dollars, pounds that you will reduce. Second, which is the saving in the bill. Third was maybe the percentage of emissions, CO2 emitted, something like that. That was the third kind of feedback. Which of these three or any other do you think which worked best? I've given you three different feedbacks. One is you save money. Second is you reduce the number of trees being cut. Third, you give the numbers in terms of the emissions, greenhouse gases emission. Or there could be a fourth one. Which of them do you think worked out the best? Save money? Okay. So perhaps you may think that maybe money is the most, you're most sensitive to money. Anyone else? So in their study, what they found out was the thing which worked the best was your neighbors are consuming lesser than you. That's it. You didn't need to give specifics on how to save energy. You just give the fact that the neighbors are consuming lesser than you. Again, when I've discussed this with some of the audience, they say that in India, sometimes you may also see the other way around. Like you may specifically buy a bigger car than your neighbor just to show off that I have the money to have a bigger car. So the dynamics may vary as per the social, but the idea is that can we do some feedback based method to help you save energy? Can we give you some nudges? Another example of nudge-based energy reduction, perhaps very pertinent, that we also have Alok from Google here. I think this was piloted at Google at some point. So foods which are very calorie rich in various Google offices, that's what I heard, they were kept slightly behind. The portion sizes were slightly reduced, the plate sizes. And that has massive impact. So you can give certain kinds of behavioral nudges and that can create a large impact as opposed to some of the other things that we've discussed. Use better architecture, get new appliances, all of which will take more time. So that is the specific area in which I'm going to be focusing in my talk, feedback-based energy optimization. So we want to give certain kinds of feedback. In this case, we are looking at this chart. If you just give a better bill, including, let's say, how much your neighbors consume, etc. So in fact, there have been studies which, just adding on to the previous example, you just give a smiley or a frown face compared to what you're doing with the neighbors, and that helps people to change themselves. But if you can make it more specific, if you can make it real time, that perhaps you've left the geyser running on while you're not using, or if you can make it even more specific, automated, very personalized to you, like your daily routine is like this. If perhaps you were to turn on the AC at this temperature from this time to this time, this is the amount of savings that you'll have. So this is the kind of feedback that we want to give. Now, how do you think we can enable such feedback? So primarily, we are looking at appliance-specific feedback. How much energy each appliance is consuming, and if you can give any specific feedback on that. So how do you think we can enable this? Sensor data. Which kind of sensor data? Okay, so it essentially pointing out to some multiple modalities of data. You're looking at the room temperature, the moisture, etc. So in fact, if you look at the air conditioning system in this room also, these have all got a control system which looks into the inlet, the outlet, the temperature, the relative humidity, all of those things are factored. But I was asking specifically for appliance energy consumption. So how do you think we can get that? Don't think about an office, think about a home for now. How do you think we can figure out how much energy each appliance in your home is consuming? Yeah, you can put a sensor on each of the appliance. What kind of a sensor would it be? Yes. So power is what times what? Voltage into current. So you need a sensor or you need an IC which can measure your current and which can measure your voltage. So that's all. You can go back to the physics and see what is needed. You just need to have the through current. So in this talk, we'll be looking at this specific concept known as energy breakdown, or breaking down the energy, total energy, into constituent appliances, or in terms of the rupee or the dollar value. You can do this at different time granularity. One could be at the monthly level. Your total monthly bill is broken down into different appliances. Or you could do at the real time. At this instant, if I'm consuming 4 kilowatt, how much wattage is being consumed by my AC, by my fan, etc. So you could do at different time granularities. So I'm also going to be referring to this concept of an energy breakdown matrix, which is this matrix where we have these homes on one axis and the appliances on the other axis. This is just a notion that I will be using throughout this talk, just to make it easier to understand. So the first way is to get this energy breakdown matrix is to put a sensor on each appliance, which is sometimes known as an appliance meter, a plug load monitor, etc. You could name it anything. So now coming to the outline of this talk. So as I mentioned, I'm going to present this around 10 years journey into this energy analytics disaggregation sector. I'll be starting off with the first thing which looks most obvious. If you want to give energy breakdown analytics feedback, monitor each appliance. So we ended up monitoring a home in Delhi. Any prizes? So no prizes for guessing whose home this is. In Delhi, did we end up instrumenting? It has to be the PhD student working on the project, right? So I convinced my family that if I install these 30 plus sensors in my home with 5 Raspberry Pis, 3 routers, etc., my PhD will complete on time, will complete quite early. Never happened. I also had, I think, the electricity utility come to me. They thought that we were cheating them. We were trying to put a fake meter and trying to not pay the electricity bills. So just didn't work out for them, for us. But this is the deployment which we did in a 2.5 story home in Delhi. This is showing the different kinds of sensors which we had. In the yellow, you're seeing geyser, laptop, air conditioner, refrigerator, kitchen outlets, motor, water purifier, etc. These are the electrical fixtures, monitors, electrical fixtures which we monitored. We also monitored electricity at the MCB level, and we also monitored one at the total home level. We also didn't just monitor electricity, we also monitored water. So interestingly, in India, there is a very nice, deep relationship between electricity and water. Can someone tell me what is it? How are electricity and water related in the Indian context? The water gets pumped to the tank using what? Electricity. The water typically comes through the utility company. It is pumped up, stored in the tanks. So water has some embedded amount of energy in it. It's basically the potential which is needed, and that requires energy to pump it up. Any other example? You also have geysers, etc., which link between electricity and your water. So these were very interesting things, especially the motor plus the pump to pump the water up and store it in overhead tank. This is not very commonly seen in the Western context. So this was quite interesting when I presented this paper. So this is the kind of monitoring I did at the electricity level. The left one is the one which got my family in trouble because the government thought, the utility company thought that we were cheating them. The circuit breaker, at each of them, we put something known as a current clamp. So you put this clamp around this circuit and it tells you the amount of current passing through this circuit. The rightmost one is the appliance level meter. So you put this sensor, which is basically an IC, energy IC, you put that into the socket and then you put your into this appliance level sensor, and then you get the energy consumed on a per minute basis. So the important thing for all of them is these are going to give you data at, let's say, every second, every minute or so. Then you have to do some logging. So therefore we ended up putting some Raspberry Pis to collect the data over them using the standard interfaces that they provide, like Modbus, etc. So we did this bunch of electricity monitoring at the home. We also did some water monitoring at the home. So this is what a water meter looks like. Now, if you noticed in the electricity monitoring, we didn't have to cut any wire. We only had to clamp wires. But for water, that provision is not that trivial. Like, those sensors do exist, but those are generally very expensive. So therefore, to fit our budget, we had to cut through the water pipe, put our sensor, and then get the flow through it. So we put this sensor again at different places in the home. We also put, as someone was mentioning, we put to get some ambient sensing, like the light, temperature, motion, sound level, Bluetooth, Wi-Fi. This will help you get a sense of, like, is there anyone in the room or not? Can we turn off something or not? So this is the sensors which we were using. Has anyone seen such kind of a sensor earlier? Have you seen any sensor which looks like this? Have you seen places where the lights turn off automatically? Have you been to such places? Many times, even in the washrooms, we have this facility. So that is a sensor known as passive infrared, PIR sensor. This is a PIR plus some other kind of sensors. So that's the PIR component here. We also, at that point of time, this is 2013, found out that the grid was very unreliable. The expected voltage is around 230 volts, but we were getting fluctuations from 180 to 250 volts. So no wonder people were putting these power stabilizers on different appliances. Now they come in inbuilt in many of the appliances, and I think the grid is significantly better at this point of time. If you were to repeat this experiment, you will not see this amount of variation. So this also brought in another interesting aspect. So in the West, when people were collecting such kind of power data, they could directly just monitor current without having to worry about voltage. Why? Voltage is typically constant, or the variation in voltage is very minor. But here we have to monitor voltage, which means that any kind of instrumentation has to become more expensive. You have to monitor both current and voltage. And then you may think that, it's what a big deal. You put 10 sensors in your home, you can just get away with it, just use that. But it turns out that homes are very hazardous environments. So very often while cleaning up the home, this would get dislodged, which means you'd lose some days worth of data. So while it seems homes are very good environments, but they are still very hazardous from a sensing perspective. This is the beautiful nightlight view I had when I was sleeping during this deployment at home. Clearly, it's not very pretty. You have these multiple routers, you have these plug computers, so this blue color thing that you're looking at is a Z-Wave controller. Z-Wave, Zigbee are different protocols. And the connectivity can unfortunately be very poor at homes. So you may think that in your home connectivity is perhaps okay, but you're thinking of perhaps very accessible spots. Think of the refrigerator stuck in some corner of your home. Will you get very good Wi-Fi signal there? Maybe, maybe not. But that's what you wanted to monitor. How much energy is my refrigerator consuming? So it has to be connected over the Wi-Fi. But homes often end up having poor connectivity. So we also ended up releasing the 70 odd days of data called IOR dataset, Indian dataset for ambient water and electricity consumption. So it's been used a lot. It's been appreciated a lot. This was also perhaps To the best of our understanding, one of its kind, largest data from India during that time. So we learned a few lessons going through this study. First, we realized that it's very hard to scale household sensor deployments. This was my home, my PhD depended on it, and even I had a hard time. So imagine doing this in anyone else's homes who will have to pay you for the sensors and who will get frustrated each time you call for support. Right? So basically, we realized that you cannot put a lot of sensors in homes. That just won't work. The second learning was that releasing data helps the community. So when we released the data set, that brought in a lot more attention than just the paper. So that's one lesson I wanted to share with all you young colleagues here. So next we thought, what should we do? So if you cannot put a sensor on each appliance, what can we do to still get your per appliance energy consumption? Any thoughts? So I showed you in the deployment that I had 3 stages, 3 spatial locations at which I did the electricity monitoring. One was at each appliance, doesn't scale. Second was at the MCB level, probably better. Third was at the smart meter level, which is just your regular meter, but can give you data at some regular intervals. So this particular technology is known as non-intrusive load monitoring. Non-intrusive as in you do not intrude into the home, you do not put a sensor in each person's home. Rather, you just want to put a sensor outside the home, which is your smart meter, just a single sensor. And then the idea is that this is the power, on the left hand side you can see the power signal. So you want to break that down using machine learning, or sometimes also called source separation in other communities, into different appliances. So this is not very different from, let's say that if I have music playing, I want to separate out the background, the foreground, the different kinds of, let's say, instruments. So it's not very different. How do you think, or why do you think this is possible? Why might it be possible to break down the aggregate into the, let's say, 3 or 4 appliances? Think about these 3-4 appliances. Is the AC and the fridge same, or are they different? From power consumption perspective, what do you think? Yeah. So both of them are compressor based appliances. You would know that, which means that they turn on and off to maintain a set temperature. But is your family more worried if you leave the AC running on or if you leave the fridge running on? AC. Why? Consumes more power. What is the typical rating of a AC? What is the wattage? Okay. No one pays attention to buying appliances. Okay, does anyone know the units of energy? Power, energy. Kilowatts, okay. So at least you're right on the order. It's 2 kilowatts, typically 2 kilowatts, 2000 watts. Fridge, until unless you have those huge fridges, it would be 200, 300 watts, 400 watts, something like that. So it's possible that you can distinguish between different appliances because each of them have a unique signature in the power signal. So the fridge, you can see again it's an on-off appliance, but it consumes a significantly lesser amount of power. Whereas AC is also an appliance which is thermostatically controlled, but it consumes a lot more power, typically 2000 watts. Fridge, in this case, the one which I had was consuming about 150 watts and all. So we wanted to basically, this is the technology that we want to leverage the different signature of each appliance. What about washing machine? How do you think washing machine is electrically different compared to a fridge or an AC? Sorry? Okay. Okay. So fridge is a background appliance. That's the first thing which everyone assumes. Like we don't need to operate on and off a fridge. Whereas with the AC, we need to turn it on and off. Similarly, with washing machine, we manually operate the washing machine. At least Most of the times we do that. And something else? Okay. So the washing machine has typically got 2-3 different modes in which it operates. Spin, dry, something else, wash, I don't know. So there are typically 3-4 different modes in which the washing machine operates. AC is typically 2 modes, compressor on, compressor off, but you can also have fan on, fan off. Similarly, fridge is also typically 2 modes only, off, compressor on, compressor off, but then there is also a defrost mode. What does defrost do? Sorry? It melts the ice. Why do we need to melt the ice? So if the coolant, if the entire supply gets fixed with ice, the operating efficiency of the fridge reduces. So therefore, you have to temporarily put in heat into the system and melt away the ice. So let's take a very simple algorithm and we will do energy disaggregation in the next 2 minutes. We'll call this specific algorithm is a very simple algorithm, combinatorial optimization. You look at the different possible combinations and see which of them matches the aggregate the best. So let's say your aggregate consumption at the home is 2000 watts. You have 2 appliances on and off, both AC and fridge, both on and off are the 2 states. If I tell you that the total consumption is 2000 watts, what is the likely state for AC and fridge? You have 4 options. AC off, fridge off, AC on, fridge on, so on. We have 4 options. What do you think? AC on, fridge off, because the sum of the 2 appliances, if you take, would be the closest to 2000 watts. This is the consumption that you have. Okay, 2200 watts. Both on. 200 watts. 300 watts. Again, similar. Yes. Assuming there is no other appliance and there is some residual power. So this is the simplest possible algorithm that we could have built. Does anyone see any downside to this algorithm? It scales what? Yes. So like what is the scaling law for this? As in, like, does it scale linear to the number of appliances? Exponential. Like exponential, because you have, let's say, some n appliances, each of them having p states. So the total number of possible combinations becomes n to the power p. So it scales very poorly in that respect. Any other downside of such an algorithm? So it treats each timestamp as an independent problem. So if my consumption today is like at this second is 2000 watts, at next second it becomes 2010 watts, 2008, 2160 watts. At that point it will say AC on and fridge on, but then again it goes to 2000 watts, it will say AC on, fridge off, so on. So it does not have any temporal consistency, which can be misleading. Like when we operate appliances, we don't operate them like this, turn on and off at every second. So that's an issue which got solved using better algorithms, including something known as factorial hidden Markov model. Essentially, in this case, for each appliance, you will assume that it's modeled using a hidden Markov model. So no worries if you don't yet know what a hidden Markov model is. Just think of it as assume that there is a temporal consistency. So going from off to on, there will be a probability. On to on, there will be a probability, so on and so forth. There will be the transition probability. And then there is an emission probability. In the on state, my power is most likely going to be normally distributed with mean 1000 watts and variance of, let's say, 5 watts. Something of that sort. So that is not interesting at this point. You can study that up later. So this whole area of NILM had existed since 1989 and even perhaps before that. So it had existed before I was born, but it seemed that it was not a solved problem. So what we did was we looked at the problems in the NILM domain we realized that it was very hard to assess the generality of these different algorithms, because every different paper would say that we have the best algorithm, we have tested using our own machine learning metrics, our own subset of the data set, so on and so forth. So this was mainly a benchmarking problem. This is the year 2013-14. At this point, we have NeurIPS dataset and benchmarks, we have DMLR, we have a lot of appreciation for benchmarks, but perhaps 2013 it was not so much so. So therefore, we ended up creating this toolkit called NALM toolkit, where we provided multiple datasets in a common format. Like this is very common these days, but it didn't exist then. We provided baseline algorithms. This is the equivalent of like what the Hugging Face ecosystem provides in the current day. And we also provided a suite of accuracy metrics. Previously, a lot of the metrics which you proposed were different across papers, perhaps best suited to get that paper published. So interestingly, this was a toolkit paper, software paper, so as to call. And when I was trying to publish this, I was also suggested by some senior researchers, this is not research. You will not go a very long way in this. This is perhaps just a waste of time. This is good engineering. So no problem in taking it at face value. This is a good intention paper, but this will not get you a far way. But I am very happy that 11 years on, we have sort of proved that this works. And interestingly, a couple of days back when we had Venkat Padmanabhan give the keynote, he also mentioned amongst the different kinds of contribution, you have a very good GitHub repository which people are looking at. So this is, I would say, one of those use cases. So this paper has now been cited above 700 times. And for us, the success story was, are people contributing their algorithms to our benchmark, which fortunately turned out to be the case. Or 12 users, 12 papers contributed state-of-the-art algorithms. We also had 16 datasets being contributed by the authors themselves in a common format. So it also fortunately ended up winning a few awards, including BuildSys 2014, BEM Award, PhD Forum at Census 2015, and very recently this SIG Energy Rising Star Award. So it's primarily based on this paper and amongst the others. So if we look at the GitHub repo, we can see this been forked about 475 times, starred 867 times, which is quite rare. I like not to be boasting about it, but I would still say this is quite rare in academic settings to be able to have a repo which still works about 10 years plus after it was initially released. But then we also said that we should keep moving this field forward. And one thing we realized was that it was very difficult to use NALMTK, even for someone like me who had developed the toolkit. So we ended up creating something known as a declarative API. Does anyone here know the difference between declarative and imperative? So declarative is where you're focusing on, you want to decouple the execution from the specification. You want to specify an experiment, but you want the machine to do the experiment. You don't want to be writing complex code to run those experiments. So if you look at this JSON schema, we are mentioning that which power to use, active power, which appliance to use, what sample rate to use, what appliances to use, what are the methods, what are the hyperparameters for those methods, what data set do we take the training data from, what data set and what time period, start to end period. So unlike the other Kaggle data sets or let's say some image data sets, etc., here even specifying the data set is hard. So therefore we ended up creating this nice simple API which decouples the execution from the specification. So this was released in 2019 and fortunately this specific repo has also been viewed very positively by the community and we have a bunch of methods. We are also updating this as recently as few hours before this talk. So we learned that NALM will help you and NALM will help you to scale better compared to per appliance energy meter, and the sustained open source efforts will help. So these were two lessons at this point. Any questions till now? So the baselines was some very basic algorithms which are like edge detector algorithms in the power time series, 1D time series. One was combinatorial optimization, one was factorial hidden Markov model. That was the before, a lot of this was pre the deep learning star era. But in this 2019 paper, we included a lot of SOTA papers which include transformer methods, which include BERT inspired methods, which also include I would say some very specific kind of autoencoder methods. This is the list of methods. Primarily, we looked at the papers which are published at AAAI, HCI, NeurIPS, ICML, etc. And the authors contribute to many of these volumes. Other questions? Okay. So this brings us to the next point. We have said that we'll now say that we can perhaps do NALM well, because now we have developed a good toolkit and we have the capability to run different algorithms. Does running NALM save you money? If I tell you that your appliance consumes this amount of energy, does it directly help you save any money? No. What do you need? Something even more specific, more personalized. Let's see how to enable that. So general NEL might give you a pie chart breakdown. Your energy AC is this much, fridge is this much, light is this much, so on and so forth. But if you want to actually save energy, let's say we'll want to have it more actionable energy inside. So we'll, let's say, fix on the fridge energy consumption. We'll look at the fridge predicted power trace and figure out that during certain times it's consuming high power. And home 2 is consuming the high power in more number of instances. So it turns out that home 2 perhaps has excessive defrost, and you want to give a very specific feedback like this. Your fridge defrost is acting up, so it's wasting about 30% of the energy. If you get the specific circuit replaced or the specific kind of action taken, your fridge energy can be reduced by about 30%. Now, is this much more actionable than telling your fridge consumes 11%? So this is what we hope to do in this specific line of work. So we want to primarily figure out which part of the energy trace tells us why the energy consumption is high, anomalous, problematic, etc. So maybe these are the length of the duty cycles. The duty cycle is when an appliance turns on and off, or the actual power usage itself. Now, in order to do this, we will have to again make, a couple of days back again, we had several speakers discuss about physics-based models as well as data-driven models. In this case, I'm going to show a physics-inspired model of the energy consumption. So we'd say that fridge is a duty cycle-based appliance. This is the power trace and the x-axis is the time. So it turns on and off periodically, the compressor. The defrost will occur every now and then, depending on how it's programmed. So whenever the defrost occurs, the power consumption will increase because it introduces significant amount of heat into the system. And whenever you introduce additional heat into the system, that needs to be removed using the cooling methods. So therefore, if you carefully notice the trace now, can you see that the trace, this particular window will have the compressor on for a longer duration. So whenever the defrost occurs, the on duration for the next few cycles will be slightly longer. And whenever you're using the fridge means opening or closing the fridge or keeping some hot food inside the fridge. Whenever you do that, again, the compressor will remain on for a longer period and remain off for a shorter period in order to maintain the set temperature. So we have looked at the defrost, we have looked at the impact of usage, and then we also look at baseline. So baseline is the usage of the fridge which is not impacted by your use. So typically in the night hours, when you're not actively using the fridge and the defrost is not happening, the fridge will remain on and off, the compressor will turn on and off in order to just maintain the temperature. So I would say that that's the baseline consumption of the fridge. Defrost energy is all the excessive energy over and above the regular energy. So the extra energy consumed by the defrost state as well as the compressor remain on for a longer duration post the defrost state. Usage energy is whenever we see that the fridge was opened and we see that there is above the baseline, there is some more energy consumption. So therefore, we have defined the energy of the fridge across three components: baseline, not affected by usage; second, defrost, affected by defrost; and third, usage energy, which is the energy above the baseline due to the usage. So the reason why we're doing all of this is when we finally do the evaluation, we want to say that if we had a plug load monitor and we'd get this ground truth appliance trace versus if you were to use smart meter, break it down using NALM algorithms, then get the trace, and you apply this feedback on the left hand side and apply the feedback on the right hand side. So on both of these, can you get comparable benefits or not? That's the overview of our evaluation method. We did this setup on a publicly available dataset from US. And this particular plot is showing the anomalous homes, fridges in red. These have very high usage energy, which means that either the valve is either the hinge of the door is broken or there is some other issue. So what we said is for these particular homes, we could have given out of the 95 homes, 13 homes could be given the feedback based on their usage energy, and if they were brought to the nominal levels, they could save up to 23% of the energy. This is using the ground truth trace. Now the question is, if instead of the ground truth trace, we were to use the disaggregated trace using NALM algorithms, can we give this exact same feedback or not? So mainly you want to look at these red dots and see that if instead of using the ground truth trace, if we were using the NALM methods, combinatorial optimization, factorial linear Markov model or something else, can you see that these red dots have now lost their position? They're not in the correct position. So we have a lot of false positives and false negatives in terms of the feedback that we should be giving. So a lot of the red homes are the ones which should be getting the feedback, but they're not getting feedback. And these gray homes are the ones which should not be getting feedback, but many of them are getting feedback now that your usage energy is high. So in short, what we're seeing is that NALM can be giving you a very good performance as per the, let's say, machine learning metrics, root mean squared error, mean absolute error. But for the metrics which actually make a difference, which is usage energy excess, for those things, the performance is very bad. Any thoughts as to why that is happening? Yeah, excellent. So essentially what is happening is that on average, the NALM disaggregated traces would be very good. But you don't care about the averages. You care about the specific instances where the traces would show some kind of anomaly. And that is very hard. So therefore, this is an important observation that we have to look at the application specific metric. I can keep doing machine learning on this for the next 30 years, generate a lot of papers. Will that save me any amount of energy? No. Rather, it will consume more energy for all the experiments that I'm doing. So therefore, I think it's important to show that we should be chasing the right set of metrics, which should be coming in from the domain, as opposed to just machine learning metrics, which is a reconstruction error. So we should be thinking about these application-based metrics. So now I'll go on to the second part of the talk, the third, fourth, fifth, sixth, seventh paper. And in this, let's go back to this diagram. So one of the goals which we also wanted to see was, while the smart meter deployments were going on at a very high speed, but how many of your homes have smart meters? One person. Just one person from Mumbai or Surat? Thane. Okay. So one person from Maharashtra has smart meters installed, despite a lot of push, or maybe a lot of you have, but you don't know. Because we never bother about it. We don't have to pay the bills. Someone else is paying the bill. We don't yet know. So it shows a picture that even though these smart meter deployments have really taken off, but they're still not available across a large number of homes in India. So we thought, could we still give some feedback for homes which do not have smart meters? So for homes which do not have smart meters, do you get some energy signals still from the utility company? Do you get a monthly bill? That's still a very weak signal, but it's a signal. So if you look at the first bar here, if we were to give some enhanced billing or household specific advice, we may still be able to help them save 4-5% energy, which is still significant because we are only looking at their electricity bill, nothing significant. That was the aim for this particular line of work. And we took it on as a very ambitious challenge, the billion building challenge. So oftentimes when such challenges are named, etc., it's also an what is it called? What is the figure of speech? Alliteration? Yeah. So billion buildings. So, and it was also to do with the fact that there are about 8 billion people in the world. So we thought that the number of buildings would be on that order. So what we said was for every building in the world, can we give an energy breakdown, at least at a monthly level? How much can we break down the energy consumption per appliance or per the main appliances? So what we're saying is that we will be looking at the monthly bills, which is shown in that second last row, 12 bills across the 12 months. And then you have various static properties about the home. Say things like the number of occupants in the home, the number of rooms that you have, the square footage, etc. So each of them gives you a very weak signal about the energy consumption of the home. Not very specific, but at least gives you something. So the idea is using all of these, we want to tell the energy consumption for homes which do not have the energy consumption on a per appliance basis. So what we'd hope is that a small number of homes across the world will have some sensing done or will have smart meter done so that we can use an ALM and get the monthly bills, monthly per appliance consumption. But for the vast majority of homes, we do not have that. So what we're also assuming is that this problem now becomes closer to something like the Netflix problem or the movie recommendation problem. You have a large matrix which is very sparse. Small number of people have watched small number of movies, whereas the large overall matrix is largely sparse. We want to fill out those entries. But this is based on a very simple intuition that similar homes will have similar per appliance usage, where the similarity we can define based on features. So let's say if we have 2 homes, 3 homes, which have 2 occupants, 10 occupants and 10 occupants. First home has 2 occupants, the remaining 2 homes have 10 occupants. Which of them do you think will have similar washing machine usage? The last 2? Because the washing machine usage will typically be a factor of the number of clothes, which will be typically be a factor of the number of people that you have. So therefore, we are trying to say in this case, the similarity in washing machine consumption could be defined by a similarity in the number of occupants. Whereas the similarity in your AC consumption could be defined by the similarity in, let's say, a peak energy bill. Because we are assuming that the peak energy bill, at least in the Indian setting, will occur in the summer. So those people who have, or the gap between the summer and the winter will likely be your air conditioning bill. So this is the kind of intuition that we're using. Now for air conditioner, the similarity would be defined on the basis of, let's say, the ratio between winter and summer energy consumption bills. So we call this approach as Gemello, which is a Latin for twin. So now again, in today's day and world, such terminologies are very commonly used, digital twin, etc. But we're trying to do this in 2016. This was published at KDD back then. So we created this matrix where we have the train homes and the test homes. Train homes have access to the entire matrix. Test homes only have the monthly bills and certain static household properties. And then the question is, we're trying to fill out the missing entries for the test homes. I'll skip some of the details. Essentially, we solve this using a very simple k-nearest neighbor kind of a problem, where for each appliance, you could define the similarity on a different basis. So we could learn that similarity function. We had static features, home area, number of rooms, number of occupants. We had monthly bills. So we could also get some features out of them, mean, max, median, range, etc. The shape tells you something, the peak tells you something, the flatness tells you something. And then it was a regular KNN kind of a setup. So again, I would be very surprised if this kind of a paper to be accepted today. So people may just shun it off as this, what is this? This is just a KNN paper. Like, what is the technology? What is novel in this? But I would still say that this was highly appreciated at that point of time. And I still think it's a very neat, simple solution, which is showing the power of what was, again, commonly during that age called big data. You have a very weak signal from a very large number of homes. That works better than a very strong signal from a very small number of homes, which is NALM. So interestingly, we benchmark this against state-of-the-art NALM approaches. Smart meter data, 1 reading a month versus 15-minute data and NILM. And we ended up beating them. So this is what I was saying as a hypothesis. Weak signal from a large number of homes ended up performing better than strong signal from a small number of homes. Secondly, we also get some averaging benefits. Like NILM, if you're trying, so it's significantly harder to do good prediction at 15-minute level and much better if you have to do roughly at a monthly level. So we would get those benefits. I will skip this and show you that R bars are the green ones, which are better than the best baseline. And we are also able to get a good accuracy even for a smaller number of training homes. So this is the kind of curve which we typically want. As we increase the number of homes, we see an increase in the accuracy, but even at 0 or very small number of homes, we still have some reasonable accuracy. But this might naturally prompt you, why are we using KNN-like methods, etc. when I mentioned that this is a matrix factorization problem, just use matrix factorization, which is what we ended up using in the next variant of the problem. And I'm showing you the motivation from the movie recommendation problem. So if you have users and movies and you have the ratings across them and you have to fill out this matrix, what we assume is that this matrix lends a low rank structure, which is that each movie can be described by a small number of factors and each user can be defined by a small number of affinity towards those factors. So if we were to break this matrix into product of 2 matrices, then we can predict the missing rating as a product of 2 vectors, as a dot product of 2 vectors. So we did the same thing for energy breakdown, where we could inherently handle missing values. So this is essentially what we're trying to do, is to fill out this matrix using existing data that we have. I will skip out some of the details. It's just that the way we need to specify this matrix. So we have 3 dimensions: homes, appliances, and time. But in order to solve this as a matrix factorization problem, I flatten out 1 dimension to make it appliance and time. So as you can see the rows, you have appliance and the time as 1 dimension and homes as the other dimension. So it becomes a 2D matrix, which we then break it down into non-negative matrix factorization problem. Any guesses as to why we're using non-negative matrix factorization and not a regular matrix factorization? Bills. So the left-hand side bills are non-negative, energy is non-negative, and typically you would also only have additive properties. The total consumption is the sum of the consumption of different appliances. So therefore, non-negative matrix factorization helps. It also helps in the sense that now you're introducing additional constraints, which is usually better if you have them in the domain. So we want to break this matrix into latent factor for months and latent factor for homes, which you then do the matrix multiplication to the reconstruction. We also introduce the static factors previously. We would fix them as the known factors for the households. This was evaluated on about 500 plus homes from a dataset, public dataset from the US, using some of the baselines from AHSTATs, NeurIPS, etc. And we were expectedly better than the previous state of the art. Otherwise, the paper would not have existed and I would not be giving this talk. Importantly, so that's one of the beauty of such approaches, very simple interpretable approaches, and we can end up learning some factors which lend a lot of meaning. So one of the factors which we learned for HVAC ended up being highly correlated with something known as degree days. So degree days, think of this as some interpretation around the temperature of that region. So therefore, without explicitly specifying anything like that, we're able to learn such, encode such relationships in the data. Now, one interesting thing which was the limitation of the previous approach is that if we were to take two cities, in this case, let's say New York and something in California, let's say San Francisco, the energy breakdown across two cities will be very different because of the differences in geography, differences in the kinds of people that live, the differences in, let's say, the building material, etc. So therefore, if we were to apply that matrix factorization on region 1, that does not work for region 2. Now, do you again do machine learning on the region 2 completely independent of region 1, or could you do something better? So it's a broader problem which would be used across a lot of applications. Something works in region 1. How do you get it to work for region 2? Do you train from scratch in region 2? Or could you do something better, leveraging something from region 1? What do you think? Transfer learning. So we wanted to do some transfer learning, but this is again not your trivial machine learning, transfer learning that we typically used to do. Here itself, what we did was something interesting. So previously I mentioned that we had this three-dimensional tensor which we converted into matrix. Here we leave that as a three-dimensional tensor. We have M homes, N appliances, T months. So we want to break this down into product of three factors: home factor, appliance factor, and season factor. So what we're saying is that the energy consumption depends on your homes, the construction of the home, the kind of people that live in that home. It also depends on the seasonality. If you factor both of these things out, we are left with an appliance factor, which we will say is region agnostic, which does not change with a region. So therefore, what we're saying is that you train in region 1, you break down this matrix, this tensor in region 1, you learn home, appliance, season factor. The appliance factor that you've learned, you don't need to relearn in another region, which means that when you have to, in a new region, learn the home and the season factor, it's a significantly easier problem. You have a better specified, more constrained problem, lesser training data required, which is the whole rationale behind transfer learning here. So we'll say that the appliance factor is region independent, whereas the other two factors depend on the region. So now we will go on to the last couple of talks, couple of papers from this. We'll go back to NILM now. So we said that we have smart meters which will be sending data to the cloud server. That's the typical setup, because the smart meters are connected to Raspberry Pi. Does the Raspberry Pi have a lot of compute? It does, but it does not still have a lot of very strong GPU compute which you require for these powerful algorithms. So currently what would happen is you collect the data, send it to the cloud, run the algorithms there, get the disaggregation, get the results back, send it back to the user. Do you see any problem in this? Would you be comfortable in sending your energy data to cloud? Why not? What is the issue in privacy? Like why would you be worried about your energy data? It can tell when the people are there at home or not. What else could it tell? So if I'm a thief, I will now know when to come and rob your home. That's one. What else? The appliances you have. Okay. So that, but why would you worry about if someone knows about the appliances you have? Sorry? Your economic status will get known. You will also get a lot of ads. You should buy this appliance. Why is that risky? Yeah, you'll figure out what appliances you use, what time do you enter the home, what time do you leave from the home, what time do you have dinner, do you have lunch at home or not. You can also figure out if someone has any health issues or not. You can also figure out what if they have taken a bath or not. So you can figure out all of those things. Imagine the kind of privacy breach that can happen. You don't want that. So in a sense, we would typically want to have applications which work without internet, which work without, where you don't have to send the data to the cloud, and you don't want any threat on the privacy. So what is the solution then? You do the compute on the site itself, but the methods are complex. So then what could we do? These are complex neural networks which will not run on your Raspberry Pi. What could we do? You can increase the edge computing power. Try pitching this to the company smart meters. They will, like, you will have to find a new job. Yes. But you're on the right track. You could either increase something or decrease something. You have told about increasing something. Could we decrease something? Decrease the complexity of the model. How would we do that? One, you could use classical machine learning algorithms, some simple decision tree, etc. But what is the harm of that? Less accuracy. Let's say you don't want to compromise on accuracy. What could you still do? Do you know about model compression? Have you heard of model compression, model pruning, these terms? So that's what we want to do. We want to run the models on the smart meter itself. What we'll say is that we want the model to use low disk space, low memory, less computationally expensive, etc. So we want to optimize the models to run on the edge. We'll be looking at the best model at that point of time when this paper was published, which was a sequence to point model. So do you understand what is sequence to point? Can anyone give me an example? So in natural language, we have different kinds of tasks there. So given a sequence, so what is a sequence to sequence task in natural language? French to English, English to Hindi, that's sequence to sequence. What could be some example of a sequence to a point for natural language? Sentiment. Given a sentence, what is a sentiment? What could be point to sequence? Text generation, describe, right? So you have these different kinds of tasks. Similarly, for time series data, you could also have sequence to point. Given a sequence of mains data, so what you're seeing on the left hand side is the mains data. You aggregate energy consumption of the home. You want to break it down into how is consuming. So sequence, let's say 10 a.m. to 11 a.m. sequence of mains power is given, and what you're predicting is 10:30 a.m. power consumption of your fridge. Sequence to point. So this is a sophisticated algorithm which consists of multiple convolution layers. While it's a sophisticated algorithm, this will also show you the state-of-the-art models are just convolution layer, residual layers, maybe some attention block in between, something like that. Not too sophisticated. So this is the algorithm. Do you think this algorithm will run on a Raspberry Pi or on smaller microcontrollers? Not out of the box. So in order to do that, firstly, we have to do some profiling. How much mega MFLOPS and what is the model size? So this also depends on the context that you take. The context, the sequence length, window length, these are the terms which we use. And as we increase the window length, the flops would increase because the convolution neural networks will now start with bigger inputs. Eventually, they will have to run more, and then you'll finally get the output. So this is about 50 MFLOPS. So perhaps not very well suited for the edge devices. So we have different kinds of compression techniques. In this talk, I will only talk about pruning and little bit about tensor decomposition and multitask learning, but the remaining we can take it offline. So the left hand side is showing you a multi-layer perceptron. So pruning means if you want to reduce the computation, you can get rid of some of the edges or you can get rid of some of the nodes. Why do you think that helps? So getting rid of the nodes is, you can very directly see the matrix size will change. So the weights matrix is essentially a matrix, right? between two different layers. So in this case, let's say matrices are of size 2 cross 3, 3 cross 4, and 4 cross 5. This is the size of the matrices that you see in on the left hand side. If you remove some nodes, like for the right hand side, the size of the matrices are 2 cross 2, 2 cross 3, and 3 cross 5, because the number of nodes have been reduced. So lesser number of computation is required. That's one benefit. But if you remove an edge, does that remove one row or column? No, that just makes it 0. So in order to get the full benefits of that, if you want to, so that's called unstructured pruning in some way, because you're just removing some edge. Whereas if you remove a node, a neuron, that's called structured pruning, because it just removes one full row and column from the matrices. So unstructured pruning will leave you with more zeros in the matrix, but you get a lot of computational benefit from that, or no? The matrix size still remains the same. Until and unless you improve on the hardware, that's not going to help you. So this is one way what we want to do. Now let me ask you, how do you think I would choose what? Let's talk about removing some nodes only at this point, not the edges. How do you think I will decide what node to remove? Okay, one is sample them. Yes. Okay, so you're right. We need to get the impact of a particular node. How do we get that impact? Activation, okay. One is, so think of when you look at a node, you have some outgoing weights, some incoming numbers. The outgoing numbers are the activation, the incoming numbers are the inputs. You could look at either one of them. You look at the magnitudes, figure out which of them have lower output magnitudes, lower incoming numbers, remove them. That's the algorithm, not super sophisticated. You could also do this on CNN filters. You could just remove some rows and columns. I will not get into this. And then when you do the pruning, there are typically two types of pruning strategies. One, you prune them in one go, like remove the 60% of the neurons with the least weight, least L2 norm of the weight vector. Or you could do it iteratively. Instead of directly doing 60%, you could do 10, 10, 10, 10, 6 times. The latter one typically performs better in practice because it gives more time for the network to readjust. So typically you start with an initial model, you prune it, you get an unoptimized prune model, you retrain or you fine tune that on the same data or on some new data, and that's how you get the prune model. And if you repeat this multiple times, you will get an iteratively pruned model. So before I show the results, what do you think would be the main takeaway from this? Will this help? Will this not help? Will pruning help? If it didn't help, I would not be presenting this. So that's the obvious thing. And then there is some other single task learning, multitask learning. I will leave that for now. I will directly show you the results. So using this pruning strategies, I can reduce the model size from 41 MB to 0.44 MB and the flops from 19.27 to 0.21. Now, at what cost? How much do you think will the error increase? 5%, 10%, 20%, 30%? 20%. Look at the numbers. It went from 13.9 to 13.04 or 14. So no change or in fact improved. 23.83 to 27.05 or 19.15, maybe improved. 40 to 50 or 42, slightly worse. 26 to something else. So overall, we can see that we have not lost a lot. In fact, in certain cases, we are better. Why? Why do you think we could get better using smaller models? What principle? We have reduced the overfitting. So perhaps the full-scale model, in order to get the best accuracy, etc., we ended up overfitting. Whereas because of pruning, we ended up adding a significant amount of regularization to the model. There are a bunch of other results, but I will not want to bore you away. But importantly, what we wanted to learn was that we can get away with 90% of the model without any loss of accuracy. So this sounds very shocking, very surprising. But if you really want to get something on the edge, there are ways and means to do this. So in fact, if you have looked at any of the TF Lite, TensorFlow Lite or similar frameworks, you can already see how well they're optimized, and you can run some very basic object detection like algorithms on very tiny microcontrollers also. So the argument parallel with the modern day technologies is local LLMs. You don't want to be sending your data to big corporations. So how many read the ChatGPT versus New York Times recent lawsuit? Anyone? Okay, just one person. What did you read about it? Okay, so I'll skip those specific details. The thing which we have to carefully, and I think we still have to read, all of us should read through that in detail. So when you now create a temporary chat in ChatGPT, or if you delete some chat from ChatGPT, by obligation, ChatGPT like systems are now required to keep all of your chats. So be very careful now when you're thinking of, when you're discussing your, let's say, personal problems, etc. You never know now. So just to set that context. So therefore, local LLMs are the way which you want. If you want to see the performance, you want local LLMs. Similarly, you want the models on the edge to work well. That's the relationship between the two things. In fact, a couple of days back, today morning, I read a very nice talk from Simon Wilson on how well local LLMs have come. I'll send that link in case there is interest. Coming to the last bit on uncertainty in NELM. So this is the NELM task which we've been discussing thus far. You start with the mains. You predict how much each appliance consumes. But here what you're getting is a point estimate. You just get AM, the power consumption is 150 watt, 400 watt, 50 watts. But if you want to derive more benefit from it, you also want to get the certainty in the prediction. Because of the model, so now, especially in the LLM era, we have seen that the models hallucinate a lot. Don't you think it would be a lot better if they just told, I don't know? I don't know the answer to this, as opposed to creating an entire thesis which you then submit and then you are scolded by your advisor if they get a chance to read through it and, where have these 20 citations come from? They don't exist. Right? So you'd rather prefer if it were told that I don't know, but it'll just hallucinate very well. So that's the idea. You want to check if the predictions made by these also come with a notion of uncertainty. Do you know when you don't know? So in fact, that was the title of the paper, that I do not know. So what we want is at this particular point, which is marked in this black dot, instead of giving a point estimate, we want to give a whole distribution around it. So it's 150 watt, normally distributed with 150 watt with a mean of 150 watt and a certain variance, so on, so that it can then derive better applications. Now, how do we get the uncertainty from model prediction? What do you think? How can I get uncertainty from a neural network? Okay. Any other ideas? How can we get uncertainty out of a neural network? How do you get an uncertainty out of a LLM? How would you get a sense of whether the LLM is hallucinating or not? How do you get to sense if a student has cheated or not, or knows or not? If you repeatedly ask them, will you get different stories from them? If you repeatedly ask LLM, and if you get a very different set of stories, you know that uncertainty in prediction is very large. Similarly, one way to get uncertainty out of neural networks is to do multiple forward passes with different random initializations or different dropouts, different nodes, etc. There are two kinds of uncertainty. One is known as aleatoric or data uncertainty. The other is known as epistemic or the model uncertainty. So aleatoric uncertainty is primarily when you have missing data or you're not able to capture the data properly. Like if you're looking at a thermometer, So the thermometer itself has, let's say, some amount of least count. So that is in some sense giving you the uncertainty in the data itself, or due to the observation itself. You're not able to clearly read the thermometer very correctly. It's not a problem with the model. So one way to get the uncertainty would be, instead of just predicting y hat, which the models predict, we predict both mu and sigma. And then we say that our prediction would be a normal distribution with that mu and sigma. And the loss function, instead of just being the mean squared error, would be a negative log likelihood. I don't know if how many of you studied that or not. It would be a negative log likelihood. And then you try to learn both mu and sigma. Or you learn the parameters of the model so that both mu and sigma can be predicted. So that would be heteroscedastic multi-layer perceptron, which means that for every different input, you can have a different sigma. Your noise is a function of the input. Sigma is a function of x. Previously, y hat was a function of x. Whereas for epistemic or model uncertainty, one way is you make multiple predictions. One way to get multiple predictions is you learn the model on different subsets of the data. So you have model 1 learned on subset 1, model 2 learned on subset 2, so on and so forth. And then you average out the prediction and get the standard deviation across the predictions. So that way you will have different models learned and you'll get different predictions from each of them. These are known as deep ensemble, bootstrap ensemble. And then there is another thing known as MC dropout, Monte Carlo dropout. How many of you know about dropout? So typically you use dropout during training. If you use dropout using testing, for each forward pass you will get a different output. Like different node will be dropped out. So you can again get the average of those predictions across them. That would give you the uncertainty through the models, uncertainty. The metric here is very important on how to quantify if your model's uncertainty is correct or not. So this is typically known as calibration error or expected calibration error. So if you look at the plot on the left, I am plotting the 90% confidence interval. Now, if this uncertainty from this model is good, then I would expect that 90% of my data points, true data points shown in blue, would fall within this 90% CI. This 90% CI you typically get from, if you assumed a Gaussian distribution, you'd get some sigma value. Like 95% sigma, 95% CI would contribute to, correspond to what sigma? 95% 2 sigma, 99.87, 3 sigma, right? So through that, so you'd want that for 90% CI, 90% of the blue points fall within that. So that's how we say that it's a well-calibrated system. If our uncertainty is very, if our confidence is very high, which means that our uncertainty bands are very thin, it means we are overconfident. We feel that the uncertainty should have been very low, but we actually have higher uncertainty, and vice versa. So without going into the details of this, essentially I think what we wanted to show was that you can get good predictions, but with very poorly calibrated uncertainties. I don't want to look at these different plots. Towards the end of the session, I think it will be a little too taxing. And importantly, the calibration across the different states has to be studied. On state, we have a different calibration as opposed to a off state calibration. Finally, I would like to end this talk by saying that we had this talk with Geo a couple of days back. So this was my whole sort of mission back then. Can we get energy disaggregation for 1 billion homes, etc. So I'm happy to say that with Geo, when we've been working, through them we have access to about 100 million homes across India through the different utility partners, where the data is available at 30-minute resolution. So it's not at 1-minute resolution or 10-minute resolution, at which typically a lot of us have been doing energy disaggregation. The signal is indeed very weak at 30-minute, because 30-minute you may have already seen one compressor cycle on and off both. But that's the hope, that we can still leverage the large quantity of data and enable very powerful analytics for a large number of homes. Secondly, we had this benchmark paper NLMTK in 2013-14, and then had a version 2 significant improvement version 2, which was NLTPK Contrib in 2019. So now we are looking at creating an annual benchmark or an annual competition. So for 2025, we are targeting that. So with this, I like to end and take questions. I know it's a lot. It's about 10 years worth work I've tried to compress in about 65 to 70 minutes. Might be a lot to digest. Okay. Okay, so I don't exactly, so the question is that you trained a model, full model, and then you pruned the model, and then did you give it the same data or not? I am not 100% sure as to what we did or what is the correct procedure. I think perhaps we had a different subset available, but I can't recall now. Yeah, but that also looks a little weird. For every iteration, if we were to use a different subset. Yeah, or maybe we just use the whole previous data again. That's also quite possible. I don't recall now. Yes, other questions? Okay, if not, thank you. We will have the next session in about 30 minutes or so. That will hopefully be a lot more interesting. That will be by Manish Jain, who leads the Center for Creative Learning. So we will hopefully convince you that AI is not the solution to all the problems and show you the joy of learning. So look forward to that. Thank you.